Okay, so I'll be continuing with my class on chemical drug safety, and we'll be looking next at what is called structure activity relationship (SAR). Okay, structure activity relationship (SAR). So SAR studies correlate chemical structure with biological activity, guiding drug optimization. So that's SAR studies. Now, the first one under SAR, that's number two. Remember, we've done number one, so this is number two. So A under SAR is functional group modification. So functional group modification. Now, so here it talks about how you can modify the potency, okay, like the strength of a drug, okay, and how well it works by substituting the functional groups. An example is penicillin, converting penicillin to amoxicillin. So we know that penicillin is one of the oldest antibiotics. Okay, so in fact, it's the oldest known modern antibiotic. And then over time, it became less potent. So an amino group was added to it to form amoxicillin, which we all know very well. So look at penicillin here. This is the structure of penicillin. And here you can see the group that has been added to it, NH2, that is an amino group. Okay. Now, amoxicillin is also becoming less effective. So new antibiotics are being made. But when you look at there's a structure, right? And just one group changes the function. Just one group changes the function of the drug. Next, B is pharmacophores. Pharmacophores. So pharmacophores is defined as a set of structural features in a molecule that is recognized at a receptor site and is responsible for the molecule's biological activity. I'll go over it again. Pharmacophore is defined as a set of structural features in a molecule that is recognized at a receptor site and is responsible for the molecule's biological activity. So that is what we call a pharmacophore. Now, example will be, remember we talked about cocaine, procaine, lidocaine, and tetracaine in class. So I'll be moving on from there. Okay. So they all have the same pharmacophore. So what's the pharmacophore for these three APIs? So the pharmacophore, if you notice, look at my cursor. The number one is lipophilic aromatic group. Lipophilic aromatic group. Then it must have an intermediate linkage, and then it must also have a hydrophilic amino group. So let's look at all of them and let's see whether they have these three uh, components. So these three components make up the um, pharmacophore for the cane family. So for instance, let's look at cocaine. So this is the structure for cocaine. So cocaine, you have an aromatic group. So this is the aromatic group here, right? You have an intermediate linkage. This is the intermediate linkage. This CO and C double bond O and CO single. Okay, so this is the intermediate linkage. You can see it. Then amino group. So amino, you have an N here. right? Amino group. So this is what makes up the cane family. Let's see whether it is present in other APIs. Now, procaine, for procaine, you can see the aromatic group here too, right? Then the linkage, you can see is similar. You have this linkage, right? Then the amino group, look at the end here, amino group. So this procaine. Let's look at another example, lidocaine. So for lidocaine, this is the aromatic group, right? This is the linkage. This is the linkage. And this is the amino group here. This is lidocaine. Tetracaine. Here is the aromatic group. Here is the linkage. And here is the amino group. So they have very similar components. And so this component or set of components is what you call a pharmacophore. Okay, a pharmacophore. Next, we look at isosterism and bi-isosterism. Okay, now to B. So that's isosterism and bioisosterism. Isosterism involves replacing atoms or groups in a molecule with others that have similar size, shape, and electronic properties. So here, you have a drug, an API, but you want to make it better. Okay, you want to create a better API. How can you go about it? So you can look for an atom or groups, okay, of atoms in a molecule, and then you replace them with similar uh, uh, groups that will give you different electronic properties. So then for bioisosterism, here you are substituting functional groups, okay? So you are substituting functional groups with others that will yield um, biological effects. So there's a drug probably, we are going to look at an example of uracil, for instance. Here's uracil. So this is uracil used for cancer treatment, okay? But to improve it, we can simply add fluorine to it, and this makes it F-fluorouracil. F-fluoro, sorry, 5-fluoro uracil. 5-fluorouracil. So 5-fluoro, just by adding this fluorine, it improves its anti-cancer activity. So the anti-cancer activity of 5-fluorouracil is superior to that of uracil. I hope you understand. So we are going to be doing some exercises on this later. I'll give you some assignments and all that. So you're going to discuss on this. Now to number 3, mechanisms of drug action. Mechanisms of drug action. So we are looking at, okay, how does we are looking at the action of the APIs in the body, how they act, okay, how they act to solve problems, okay, to cure diseases, to manage diseases, okay. So the mechanisms of action. So that's 3 now. So A is enzyme inhibition kinetics. Enzyme inhibition kinetics. And there are two types. You have competitive inhibition and irreversible inhibition. So competitive inhibition means that they compete with some enzymes in the body. That's how they act. And in some instances, they can completely change some enzymes in the body, like aspirin. Aspirin will acetylate your cyclooxygenase. So they completely change some enzymes here, they compete with the enzyme. So those are two ways they can go about it. So that's A. Two is what we call receptor binding and activation. So for receptor binding and activation, you can have the active binding to an enzyme or a receptor in the body, and when it binds to that receptor, it activates it. So by activating it, it can either increase the production of a compound that will solve the problem, okay, or it can even help to enable some processes in the body. But what it does is it binds to a receptor in the body. Then we have what called the third mechanism is DNA RNA interaction. So here it interacts with your DNA, okay, and when it interacts with your DNA, it forms cross links. And by forming cross links, so it can actually help to solve the problem. An example is your cisplatin or doxorubicin. Next, membrane disruption. This is very common. So membrane disruption. So and here, in fact, a very good example will be your um some antibiotics, antifungal medicine. Even your penicillin, amoxicillin, that is how they work. Okay, for penicillin and amoxicillin, they stop the bacteria from repairing its walls. So the membrane, the bacteria will not be able to repair its walls because as the bacteria is moving around, its walls will be broken, its walls will be damaged. So it repairs it very fast. It keeps repairing the walls very fast as it's moving. But when you use your antibiotic, it prevents the bacteria from repairing its walls. And because it cannot repair its walls, the contents of the bacteria will leak out and the bacteria will die. So that is how it works. So the same with here, you have amphotericin B. So it binds to ergosterol, forming pores in fungal membrane. So here it forms holes in the membrane of the fungus and thus kills the fungus. Another important mechanism is signal transduction pathways. So for signal transduction pathways, we have an inhibition of, we have pathways in the body, right? So these pathways support both our nervous systems and many other systems in the body. Okay, so if you have, even when it comes to pain, pleasure, and the way we feel, so but if you want to stop a particular um, uh, problem, you can simply block it. So you have that with some analgesics and all of that. So you can block some pathways. So like all those some of these pain relievers, they do the same. So take note of that. So my next class will be on drug receptor interaction.